So I studied artificial intelligence and mathematics in Canada. I did a degree there. I didn't do my master's, I just did a bachelor. And that was way back in 2015. AI was a lot different in 2015 than it is today. I'm going to talk a little bit about the journey from that year to where we are now. My journey is I graduated from university in mathematics computer science. I went on to work for DARPA, which is a military contractor in the United States, and I was building neuromorphic chips for a while. When I was doing that, I got fascinated with Bitcoin back in 2016, and then I started building Bittensor almost 10 years ago. In that time, I went to work for Google. I was working for Google Brain, which was at the time the premier AI research lab in the world. And then I quit that job and started this network. It's a digital currency network. In 2021, I live in Peru, and this is really my life. So it's a pleasure to come and speak with you guys today and talk about what Bittensor is. But I'm not here to sell you guys a digital currency. We're not going to be talking about prices and bullishness. I want to talk to you guys about the fundamental ideas of why this intersection of artificial intelligence and digital currency exists, and why you should care about it. Whether or not it's Bittensor or any other project. If they're doing it properly, it's interesting. So let's go back. Okay, yeah, here. Okay, so this is in 2010 when I was just graduating from high school. We were still even in 2014 and 2015. We were still working on MNIST. Who knows what MNIST is? Do you guys know? You don't even know he knows what MNIST is. MNIST is a famous benchmark. Geoffrey Hinton and Yann LeCun used it to create the very first neural networks. But back in 2010, this was before the deep learning revolution. AlexNet is not until 2012. And in 2010, the way in which we were doing things like detecting handwritten digits, whether or not this is a 1 or a 2 or a 3 or a 4, it was done. This is an example of a paper from 2010. Curved straight line analysis. So they would try to try to find lines and curves, and then they would write a mathematical function that could map the number of curved lines, the length of the curved lines, to whether or not it was a 1 or 2 or 3 or 5 or 6. And they got 97%, which is actually really shitty. So if you take a standard, like 2-layer neural network right now, you can get like almost 100% if you know what you're doing. So the field has come a long way. And it wasn't in 2010 that AI became popular. If we'd done a lecture on AI in 2010, none of you would come. It was like boring. It was SVMs. No one knew it was happening. It never worked until this page. Until AlexNet in 2012, and the innovation was that instead of pre-encoding the representations, we let the model learn what to look for inside of the image. So we built a neural network, we defined an objective function, the error rate, and then we adapted the weights using gradient descent and had the neural network learn which representations were valuable for detecting a handwritten digit. Now, this was a massive moment in the development of artificial intelligence. I was at university, I remember it, because we crushed MNIST. And then this was really, the field has not been nonstop since then. And the reason why it's been nonstop since then is because we discovered a structure a different type of structure for approaching these difficult problems. Instead of encoding the solutions, thinking really intelligently about what a handwritten digit looks like, we were going to learn it in a process of adaptation. You take the weights of your neural network, you output the loss by, you take data, you put it through trials, you get a loss, and then you adapt the weights with a gradient. So this is like a loop, right? And you just let it run. And over time, the loss decreases and your neural network works. Now this pattern shows up all over the place. It also shows up in reinforcement learning. All the rage right now is using RL for getting better. Like the latest GPT-5 was trained with RL fine-tuning as its last stage. What made GPT possible was PPO, policy proximity optimization, RVLH. All of these algorithms, reinforcement learning is a type of machine learning that is very similar in the structure. There's an environment, an agent acts in the environment, and then a reward updates the parameters of the agent, right? Again, notice the similarity. There's a feedback loop, right? And we can run this feedback loop a billion times. And how this is different than the way we were thinking about the problem in 2010 and before. In fact, before 2010, there was such a long period of no advancement in artificial intelligence that they called it the AI winter. Now it's hot outside right now. Genetic algorithms, you guys are probably studying these. It's a very similar structure. There's a genetic code. We evaluate it against an objective, and then we select the population. And slowly but surely, this gets better and better. Very similar concept. We can see this in nature as well. So there's a very interesting experiment you can do with an organism called a slime mold. You guys know what a slime mold is? You probably eat it in China. Yeah. But what's not the taste is not the interesting thing. Slime molds. What you can do is you can put them inside of a maze and put oats on the other side, and the slime mold will follow the gradient of smell. It's not exactly smell, but it can smell the protein in the oats, and it will grow and contract until it finds a way through the maze. It's very simple. Let me see if I can actually. Hold on. I can get a video up of this in a second. Very cool. We could look up, maybe we'll do it at the end. But there's actually a video you can watch of a slime mold beating a maze. And it's exactly the same structure. So the tendrils expand. The ones that are closer to the nutrient, they get selected. And then the slime mold follows this process of adaptation to a reward that is very, very powerful. And it's like the simplest form of intelligence in biological systems that we study. I'm going to go even deeper for you guys. Matter itself. Everything in nature also follows very similar structure, similar patterns from the way in which a tree grows to a leaf to even lightning bolts behave this way, and river deltas, where you have structure that gets energy and adapts itself to maintain its energy. One way to think about us as biological organisms is the same thing. We're basically energy adapting or structures that try to find energy so we can sustain our structure. And if we can't, we die. So this goes all the way down to the absolute core of structure inside of the world. And that's really what we're tapping into with the modern machine intelligence. There's a pattern. All these things are one thing. State, objective, feedback, adaptation, a loop, and things move quickly. Okay, but why am I telling you all this stuff? Because we're not talking about just AI. I came here under the premise of, I think it's AI plus crypto is the topic, right? So why are we talking about this at all? So when I was studying neuromorphic chips, I was studying this behavior sort of with the American military. At the time, I was learning about Bitcoin. And I came to the realization that Bitcoin was also an example of this phenomenon, not as a currency, but as a network. That Bitcoin is a self-adaptive computer, a network that produces hashes, and it actually does it really, really, really powerful. It works like this. So in Bitcoin, the miners produce hashes, the network rewards them in BTC, checks the hashes and sees how fast you produce those hashes, and it rewards you in Bitcoin. That's how Bitcoin works. And they use this structure, this computational structure, to secure the network. I won't get into it later, but basically, Bitcoin is constructed as a self-adapting system that produces hashes according to a very similar structure that we talked about on the previous slides. Now, why is this interesting? It's interesting because Bitcoin is the largest supercomputer in the world. Let me repeat that. It is the largest supercomputer in the world. It is actually 1,000 times larger than the computing power of all the 6 largest compute providers in the United States. 1,000 times larger. It is so big, it produces 10 to the 21. That number is so large in terms of hashes that it probably wouldn't even fit on the screen. To give you another idea of how large it is, it consumes 23,000 megawatts of continuous draw. It's the same electrical draw as Thailand. It consumes as much electricity as a country with 100 or so million people in it. Just a network. It is so large that, it has to be so large because if it's not large enough, it can't be resistant to governance, but that's a different governance, that's a different conversation. It basically is perfectly efficient. As the price of Bitcoin goes up, the miners produce more hashes, and this is why it's very interesting to think about it as a computer. I'll give you another analogy. Take the 6 largest compute providers in the United States. For about $1 trillion, they produce about 1,000 exaflops of compute across all of them. Bitcoin, for somewhere between $50 to $300 billion, I can talk about how I estimated that later, produces 450,000 exaflops of compute. 450,000 exaflops of compute. Just to give you guys a matter of perspective, that's somewhere between 700 and 9,000 times more efficient at producing hashes than standardized companies, right? Thinking about Bitcoin as a self-adapting computer, the reason why that's the correct framework is because what we're seeing is the same type of exponential efficiency and scale and improvement that we saw with the advent of things like AlexNet in artificial intelligence, but we're seeing it again in a network for computation. And that's because Bitcoin is really something like it's kind of like a program. It's kind of like a machine learning algorithm or an optimization algorithm, genetic or neural network or RL reinforcement learning. It's very similar in structure to these things, but it's applied to creating this thing that's called it's a digital commodity. Now, why is it so powerful? Why does this work so well? So Bitcoin is the first ever example of this in nature. We've never really produced anything like this. There's no network that can compete in scale to Bitcoin. But let's talk about some of the qualities that this type of optimization has. This type of qualities that Bitcoin has. One of the nice qualities is that Bitcoin is borderless. Doesn't matter where you are, you can mine Bitcoin with your laptop. Allows you to get access to resources in every country on Earth. That's pretty cool. It's continuous. It doesn't have a a start or a stop time and doesn't close on weekends. It's not like seminars or seasons in a school or the U.S. stock market that closes on weekends, or there's a league and there's a season for the league. It's 24/7. It's all the time. It's very, very competitive, and it's always optimizing itself. It's fully autonomous. It's permissionless, means you don't have to ask anybody to participate in this system. It simply draws as much electricity from the grid as it can. A normal corporation can't achieve that form of efficiency because it needs to have an HR department. It needs to see who you are. There's going to be bias. Where did you go to school? Bitcoin doesn't care that you guys went to the best university in the world. Sorry. Bitcoin does not care. It just cares if you can produce hashes. And that's what makes it so efficient. And then the final point is that it's a pure market for something. If you can produce more hashes, you get paid for those hashes, and it allows you to allocate a lot of computing power to the network and know exactly what your return is going to be. And so Bitcoin is a really effective market in the sense that it can produce these hashes with efficiency. And I just want to say that it's this new type of computing, which I'm going to label incentive computer. Bitcoin is just like how machine learning is a type of computing, and reinforcement learning is a type of learning, and genetic programming is a type of computing. Incentive computing is also a type of computing that we should study, and we should think about. How can we do it properly? How can we do it generally, actually? Because we don't want to produce hashes, we want to produce anything. Hashes in Bitcoin are useless. But what if we could take the same premise and we could apply it to storing files, generating compute, or doing machine learning itself? What if we could apply the same premise that created the largest supercomputer in the world, what if we could apply that same premise to, hey, training machine learning models, for instance? Or really anything, actually. So what's the general incentive computer? We did this. We basically asked that question, and we broke apart the way in which Bitcoin works. The miners produce hashes, the validators check the hashes, the network emits to miners. We built the general version of this. Miners do any work, validators check any work, and the network mints a digital currency to those miners. We called that thing we called it Bittensor, and fundamentally it's just it's a platform where you can create this new type of machine learning. It's basically it's like a torch. It's like a language for creating incentive computing. It's a language. So how does this work? It looks a little bit like this. That probably doesn't mean anything to you guys, but the idea is very simple, very similar to Bitcoin. You register a miner. That's going to be associated with a cryptographic key. And then you do some work. You do some work which is consumed by the validators, the people that check your work. They check your work according to some rules that are predefined. And then the results are given to the chain, and the chain reaches agreement on which of the miners have done well. So like this is a little bit what that looks like. When the top here, these are all miners. Each one of the green dots is a miner. And they're providing something of value to the network. Maybe it's storage or compute, for instance. The validators are checking how much they're bringing to the network. And this is their ranking. This is how well they perform. So every mechanism on the network of Bittensor has some sort of curve. Hey, these guys are doing better than these guys. It ranks them and then pays them out based on where they are on the curve. And there's a video here, but I can't show it right now. I should have taken a video before to show how over time we basically cycle and we churn out the bad miners and replace them with new miners. It's an adaptive system. It's a genetic algorithm or something like a reinforcement learning algorithm. Maybe you even think of it as a machine learning gradient descent problem. There's a lot of different ways or similarities to think about it as an optimization problem, but over top of any general productivity on behalf of miners. So let's take that apart. What's an example? So this is a company. It's also a network on Bittensor, and their focus is to mine coding intelligence. Bitcoin for being good at programming with cursor, basically, right? So intelligence models. They're looking for the people to mine improvement upon benchmarks that are valuable to agents that code. So basically it looks like this. The miners are agents. They produce agents. Those agents are evaluated on a benchmark. And then the reward is paid to them in some token, digital token. This is the performance of that mechanism, that optimization problem, over a 3-month period. This is the performance on Swebench. This is the number of agents that are currently being evaluated. And here, this is the performance of the agent, the best agent, on the network over this 3 or so month period of time. As you can see, the mechanism didn't define the solution to the agent. They simply encoded the incentives under which the agents could be evolved. Let me say that again. We did not make a machine learning agent. We simply defined the incentives under which those AI agents could be evolved. And in a short period of time, we beat the best in the world. So this is the agents that came out of this network are better than Claude, OpenAI, any model that is closed source or open source at doing coding challenges. Who did it? We don't know. Somebody some random person in the world wrote a 7,000-line piece of code, 7,000-line AI agent that was capable of embedding files, grepping files, applying edits using Git to improve the performance on Swebench. It really clicked, and this is like this. For me, is very similar to what it felt like in 2012 when we were able to get neural networks to finally work, and we saw their performance, their ability to crush benchmarks in a way that had not been done before. This is an AI lab without any engineers. This is an AI lab that doesn't define any specific problem, doesn't define the way in which problems are solved, but in fact solely defines the incentive. So this is an ongoing project, by the way. If you're interested, if this is something that you'd be interested in contributing to, you don't need to ask me any questions. It's an open network. It's a permissionless network. We have some ex-miners in the crowd. Hey, Nick. And the reward is quite substantial. Because what we do as an AI company is instead of raising all this venture capital and then hiring HR departments and doing marketing, we just put all of the capital, all of the money straight through the network to the people that are actually doing the optimization, the people that are actually solving the problem. So if you're a miner on this subnet, for one day you can make $60,000, which is quite a significant amount of money. And you don't need to ask anyone for permission. Let's go to a different type of problem that is very interesting and relevant to open source artificial intelligence. For us to be able to build neural networks that really matter on the grand scale, we need to be able to train massive machine learning models. And without tens of thousands of GPUs at our disposal, it's basically impossible to compete with closed source labs. But if we can combine resources from you and me and Etienne and Nick, if we can all combine resources, then we can potentially train a machine learning model that is as big, and we don't all have to carry the same economic load. What if we could build a market for the gradients that are required to train that type of model? What if we could structure an optimization problem for an optimization problem, which is the production of gradients relevant for training a machine learning model? So something like this, What if we could have a market where we say, hey, produce me gradients. We're going to check whether or not the gradients reduce the loss, and then we'll pay you out. We did that. And this is the result. This is the current training run, the current largest. We're training a 70 billion parameter model across the internet. It's permissionless. Anybody can contribute anywhere in the world. There's no whitelists. We don't ask questions. And we pay you for being able to produce a gradient that reduces the loss faster than somebody else. This is Bitcoin mining to training machine learning models. This is the largest. This is a fully decentralized model. It's across the internet. It's incentivized. It's permissionless. It's never been done before. And we did this on Bittensor, and this model is going to be done in a couple of weeks. I think it's actually quite interesting. This is something I care deeply about. We also work on more standard or well-known problems in the DPIN space. For instance, like GPUs, whether or not you can mine the network by contributing GPUs. We check to see if the GPUs are legitimate, and we pay you out. Now, this is kind of a simpler problem. It's not as sci-fi and not necessarily as AI, but it's also very cool what we can do. We can take this mining structure and apply it to a digital commodity, or this is actually a physical commodity, and have the miners all around the globe, some Chinese miners, for instance, contribute GPU resources, and they can be rented off the network because all we do is verify if the GPU is legitimate. These prices are the cheapest in the world. Because we built this network in a permissionless, borderless, and incentivized way, we get the cheapest rate on GPUs anywhere. Let's talk about some of our other successes. This is a working product built on top of our network. A similar idea. Well, it's the same idea. The miners need to provide inferences. So they need to provide an endpoint that can accept queries, and then we will check the speed, how quickly you can run that software that does the inference, and we will pay you your reward. In short order, we are the largest provider of open source models in the world on Open Router. So we provide this network that's run via contributions from people all around the globe runs more inferences than any other open source provider in the world. At one point, it was providing more inferences for DeepSeek than DeepSeek itself. I can go on, and I'll give you one more. For those that are interested in robotics, not only can we optimize these kind of abstract digital things like gradients, and compute power, this kind of incentive computing domain is very broad because we're dealing with real incentive, not like reward from a machine learning perspective where it's just kind of a number on a computer. We're talking about real money, real physical money, maybe humanity's most abstracted form of energy. And because of that, we can actually optimize things that are both physical, digital, and everything in between, from chips to GPUs, to gradients, to software, and also robotics. So for instance, we are optimizing, we're having miners contribute machine learning models. Those machine learning models are checked for performance, and then we give them a reward, and we get things like, for instance, this is this showing? This is a drone that is running a machine learning model inside of it in simulation, where this machine learning model has been provided by people to the network and measured in the performance on a set of environments. So basically, it's like this is the trajectory of that machine learning model, and we reward the miners for producing internal architectures that can, machine learning models that can run these courses very fast. So we're also optimizing things in the physical world, but the list is long, really. This is 9 other projects on Bittensor. In the top left corner, you can mine Bittensor by trading in the stock market and performing better than others in producing signals for the trading in the stock market. You can mine Bittensor by betting on sports. You can mine Bittensor by training vision models like VLLMs that can detect moving objects. Very valuable for sports. In the top right corner, we have AutoML. So we have some of the best automatic machine learning architectures in the world. So basically scripts that can automatically train machine learning models. And the list goes on and on, from drug discovery, weather prediction, Bitcoin prediction, quantum computing, Bitcoin mining, 3D image generation, data understanding, inference speed, and commodities trading. We applied this idea of monetary optimization to ourselves. Just last year, we took the network and we said, hey, if you can build a mechanism and that mechanism is itself valuable to a market of other mechanisms, we will reward you with liquidity. So we said, hey, let's take this even farther. Let's apply reinforcement learning to itself. This is like 30 of the top mechanisms on Bittensor. There's actually 128 of them. So we built a mechanism called dynamic tau, where we basically provide liquidity to mechanisms that are running on Bittensor based on their ability to maintain high prices and to consume or sequester tau in the ecosystem. All of this is basically us applying ourselves to ourselves. Now, but why? We're moving into an era, probably for the first time in history, that some of the largest companies to ever be created only have 1, 2, 3, 4,000 employees. OpenAI, $100 billion company, possibly the next mega unicorn, they only have 3,000 employees. It's controlled basically by one person. It's a closed source lab. You'll probably never work there, and for the rest of your life, you'll have a subscription. All the power for a very small group of people that they make decisions, and ultimately you don't even know what's happening. You don't know where your data's going. There's some shady shit there. You're not participating in it. You don't own any OpenAI because it's a closed round. This kind of top-down world where artificial intelligence gets pulled into a small set of really small companies, and they control all of the compute and all of the data, and there's nothing that you can access. That's where everyone wants us to go. But as a consequence of us approaching these problems with this new and very powerful technology of a monetary optimization, we also are distributing ownership, making the games transparent. Everyone can participate, you can own, you can contribute, and you can access these digital commodities in a different way, in a more fair and open way. So that's why we're really doing this, but I didn't really talk too long about that because here we are in an academic setting. Anyways, yeah, so that's the end of my presentation. I hope that that was interesting for people.